In problem 2.9, we are told to find the expectation value of the Hamiltonian and therefore the energy at time t equals 0 using the old-fashioned way, which is this function, the integral of psi x comma 0 star h hat psi x comma 0 dx. And this is sort of the original method that we use to find the expectation value of things, where we said that the expectation value of any operator, q, would be equal to the integral of psi star multiplied by the operator of q, q hat, acting on psi, and then dx. So we're being asked to use this method here and sort of compare and contrast it to the method we used in example 2.3, which involved sort of taking advantage of the fact that the magnitude of Cn squared was equivalent to the probability of being in some given energy level. And basically what we're being asked to do is we're being asked to find this, or being asked to find h, the expectation value of h, and we're being asked to sort of ensure that the result that we get is in fact equal to the result we get in example 2.3, which is sort of this result, 5h bar squared over ma squared. And this is sort of an indirect proof of something that we sort of stated without giving any justification for. Because earlier on in this chapter, one of the things that we sort of said was that the magnitude of Cn squared is equal to the probability of being in some given energy level upon measurement. And we didn't really prove this. We kind of just stated this and sort of just asked. Griffiths sort of stated this and just asked us to accept it. And it is correct. However, sort of we weren't really told why. This isn't, in my opinion, it's not a very good proof, but it sort of does mathematically show that the two are in agreement. So it sort of works, it's sort of slowly working its way towards actually proving it. So this is just sort of a very nice sanity check we can do just to make sure that this claim that we made earlier when actually going over section 2.2 is in fact true, and that these coefficients for the completeness theorem actually do give us sort of the probability of being in each individual sort of separable solution state. So let's just do this problem. So this is the wave function that we have in example 2.2. We have psi of x comma 0 equal to some proportionality constant or some normalization constant, big A, multiplied by x times little a minus x. And our sort of wave function goes from x equals 0 to x equals a. And we solved for the normalization value, big A, in example 2.2 to equal square root of 30 over a to the power of 5. So if we're going to use this traditional method that we sort of derived back in, I think, chapter 1, the first thing we have to do is we have to define the operator h hat right here. So we already know what this is. This was sort of given to us, but h hat is equal to the kinetic energy operator t hat plus the potential energy operator, and we'll call this v hat. And we defined this way back to equal negative h bar squared over 2m times second partial with respect to x squared. And this is added with the potential energy of our system, v of x comma t. And here actually we can just straight up say v of x, because we're already assuming with these sort of separable solution systems that v is time independent. So let's plug this right in. So by this formula right here, the expectation value of the energy, or the Hamiltonian, is going to be equal to, and we already have psi, and we have psi star. Psi star and psi have to be equal because there's no complex terms in here, so the complex conjugate doesn't actually change anything. A just gets multiplied by itself, so we have 30 over a to the power of 5 at the front. And then we have our integral going from 0 to a, because our wave function is only defined in that range. And we have psi x comma 0 star, which is, since psi of x comma 0 star and psi of x comma 0 are equal, this is just x times a minus x. And we have the operator, negative h bar squared over 2m times the second partial with respect to x plus our potential, v, multiplied by, and I'm actually going to distribute this out fully, a times x minus x squared, because that way it'll be more intuitive to sort of just do the integral without showing our work. And this whole thing is multiplied by dx. So let's sort of work this out. First off, our potential, v, we sort of defined earlier on to be equal to 0 because we're dealing with an infinite square well, remember? So for an infinite square well, v is 0, so this automatically goes to 0, so we can just remove it. And everything else automatically gets brought into here. And now we have a second derivative acting on this polynomial, ax minus x squared. And so this is going to give us, so we have everything at the front, it's still the same, so 30 over a to the fifth times this whole integral. And now we're going to be multiplying by negative h bar squared over 2m as before. And the second derivative of this polynomial, which is going to just be negative 2. dx. And from here, everything is still the same. Sort of these positives, these two negatives cancel out to make a positive. The 2 here cancels out with that to bring everything sort of closer. And we have, let's see, 30 h bar squared over ma to the fifth. And we have an integral from 0 to a of ax minus x squared, again, where we're sort of distributing this first term. And this whole thing is marked by dx. And now, this is just a very trivial problem of doing this integral. We have 30 h bar squared over m a to the fifth. And we have, let's see, a over 2 times x squared minus 1 over 3 times x cubed, evaluated from 0 to a. So that means we just replace all of the x's with a's, and we have this term going to, let's see, a cubed over 2 minus a cubed over 3, which gives us a cubed over 6, I believe. Because that's 3a cubed minus 2a cubed. That's 1a cubed and 6 on the bottom. Yeah, that's correct. 6 cancels out with the 30 to make a 5. And then we have a cubed on the top canceling out with the a to the fifth to make it squared. So this finally gives us 5 h bar squared over ma squared. And if we look back, this is exactly, we're matching. This is 5h bar squared over ma squared. We have 5h bar squared on the ma squared on the bottom as well. So we have verified that this is true because we've linked these two solutions together, and they are in fact the same, and therefore this is the answer.